Hello, and today's lesson is about area under the curve. So before we get to that, I just want to go back to derivatives. So we spent many units on derivatives, but the first thing we did is we learned our derivative rules, right? So we had that unit 3 in derivative rules. Then we had several units after that about the applications of the derivative rules. So once you learn the derivative rules, then you can go into the applications. So some of the applications we did with derivatives were finding the equations of tangent line, all those rate problems, related rate problems, optimization problems. So once you learn the rules, then you can go and look at the applications of them. What does that have to do with the integral unit? Well, it's the same idea. We spent a couple lessons learning about integrals and antiderivatives and the rules. And now that we know how to integrate, now we can look at the application. Well, why do we need to learn how to integrate? What's the purpose of that? So one of the applications of integrals is finding the area between two curves. And that is done using definite integrals. So we learned what a definite integral was last lesson, and we learned how to work with it. And then now that we know how to get definite integrals, which is our fundamental theorem of calculus part 2, now we can apply that and use definite integrals to get the area between two curves. So that's the connection between how we learn rules and then we'll learn the applications of it. Remember, calculus is more the real life math. It's not as neat and clean and easy and simple as it was in high school, but it's more real life and more realistic of what you encounter in the world. So we're just going to do two examples together today. They're kind of simple examples, and then I do have that video that I want you to watch where they go through a little bit more complicated examples and explain a little bit more of the theory. So between this video and the other videos, you should have enough to do your assignment and be able to do all the examples off of the old exams. So area between a curve. So our first example is from the textbook. So it's on page 349, number 2. So your textbook already gives you this graph, so they start you off with a graph. So in this graph, you have two graphs connected. You have y equals 2x, which is a line. And then you have the parabola y equals x squared minus 4x. And then the textbook says, we want to find this area here. So the area between the two curves, right? We still call this a curve even though it's a line. So what's the area, the shaded region here? So to do that, we are going to be using definite integrals. And we're going to do it, what you do is you take the top graph minus the bottom graph. So the graph on top minus the bottom one, and then if you integrate that, that gives you the area of the curve between the two curves. So it was nice that they gave us the graph. We can see which is the graph on top, which is on the bottom. So you take the top graph minus the bottom graph. So the top graph in this case was the line, 2x, and the bottom graph was the parabola. So if you look at that, in this section, the line is on top, the parabola is on the bottom. So you take the top graph minus the bottom graph, and then you integrate it. So it's really just definite integrals. If you did your homework from last lesson, you can easily do area between two curves, because now we're just integrating using definite integrals. So how did I know that the limits of integration were 0 to 6? They didn't tell me that in the textbook, but I look at the graph. We start at 0 and we end here at 6. So this gives you the limits of integration. We're integrating from 0 to 6. So we can see that visually from the graph. That's where we got the limits. Okay, now we just integrate using the rules that we've been using for the last few lessons. So the antiderivative of 6x would be 6x squared over 2. When we integrate this, we get minus x cubed over 3. And again, our limits of integration are 0 to 6. And then I can clean that up a little bit. This gives us 3x squared minus x cubed, and we're integrating from 0 to 6. The rest is easy. I've pre-done some of the work because this is exactly what we did last lesson. So 3x squared minus x cubed over 3, and we're integrating from 0 to 6. Now we just, what do you guys like to say? Plug and chug. So you start with the 6, we replace our x's with 6. And from that, we subtract when all of our x's are 0. And that's a nice one because you can tell right away that's all going to be 0. So that makes it a little bit easier, but it's not always 0. Sometimes you do have to work out both and then solve. So if I work this out correctly, 3 times 6 squared should be 108. Minus 6 squared over 3 gives me 72. And that's all just 0, but if you want to put that in. So the answer is 36. So that's how you get the area between the two curves. The first part is just connecting the graph and getting that starting point, but the rest, that's easy, just solving with definite integrals. Okay, the second example we'll do in your textbook, the graph wasn't given to you. I've pre-drawn the graph. All they do is they ask you to sketch and find the area between the two curves, but instead of the graph like they did in that last example, they just give you the equations. Y equals x squared and y equals 4x minus x squared. Hopefully we know this is a parabola. That was the basic parabola back from grade 11 pre-cal, y equals x squared. To graph this one, I just rearranged it and then factored out the minus x, so you can clearly tell the intercepts are at 0 and 4. That's where I got 0 and 4. Because it's negative, we know it's going down. So those should be easy graphs for you to do at this point. Then the area between the two curves would be this region here. So we had to do our graphs. That's really easy. The area between the two curves, this is where we're solving for. But they didn't give us the limits of integration. We had to figure out, we know it starts at 0, but what's the upper limit of our integration? So there's a little bit of extra steps on this question that the last example didn't have. Again, we are going to do top graph minus bottom graph. So when you look at it, this region, the top graph will be the 4x squared minus x squared. The bottom graph is the y equals x squared. So always make a sketch or a graph of it, same thing, sketch, because you can clearly tell the upper and lower graphs. Okay, but before we get to our definite integrals, how do we figure out what the limits of integration are? Well, you set the two equations together. So you set y equals x squared to y equals 4x minus x squared. This is easy. This is just basic grade 11 pre-cal. You set them equal, combine like terms, factor them. So your limits of integration were 0 and 2. So if they're not given to you in the question, graph it. We could see the 0 from the graph, but the 2 we had to do some work because we couldn't quite get that from the graph. Okay, now the rest is definite integrals. So you can probably finish up the rest. You don't even need this video anymore. We integrate top graph minus bottom graph. Like I said, visually you can tell that the 4x minus x squared was the top graph on the previous screen. The y equals x squared was the bottom graph. So then 4x minus x squared gives us 4x minus 2x squared. And that's what we integrate. And our limits of integration are from 0 to 2. This is really easy for us at this point. So when we integrate, I just rewrote at the top. So to integrate that, this gives us 4x squared over 2 minus 2x cubed over 3. And we're integrating from 0 to 2. We can clean that up a little bit. 2x squared minus 2x cubed over 3, integrating from 0 to 2. Again, we start with the upper limit. So first we replace all of our x's with 2. And then from that, we subtract when all of our x's are 0. Again, this is nice because 0, we know this whole thing will be 0, but I'm still showing you because it won't always be 0. Sometimes you will have to work through all of this, but that's gonna be nice and easy. That will be 0. If I've done all of this correctly, this should give me 8 minus 16 over 3 minus 0. And if I work that out correctly, it should be 20 over 3. Okay. And there you go, that's area under the curve. And, oh, no it's not. It is 8 over 3. Hopefully 8 over 3 is correct. You can check my math over there, but I think it is 8 over 3. Okay, so close, almost had it right. But the steps are correct anyways. So like I said, these are two kind of simple examples. They at least show you the steps along the way. Make sure you watch the other video that I've left you because they show you a couple other different situations that come up. But the steps are always the same. You graph it, you figure out the limits of integration, and then you're just solving using definite integrals like we did last lesson. Okay, so good luck with area under the curve today.